So problems 3 and 4 are asking you to apply the definition of either convergence or of divergence to infinity for one of the three sequences that you've been given here, or either the A sequence, the B sequence, or the C sequence. And so the first step in each of those processes is to decide which one of these three sequences actually meets the definition that you're going to be working with. So in problem 3, you have to pick which one of these sequences is convergent. In problem 4, you have to pick which one of these sequences is divergent to infinity. So let's talk about that bit first, and then our real work in our next class is going to be working on going back and structuring these proofs. In problem 3, how did you choose which one of these three sequences was in fact convergent? First of all, which one did you say was convergent? First one, the A sub n sequence. Okay, well, why might we choose that sequence? And this answer is probably not going to come from our class. This answer is probably going to come from a class you may have had 2 or 3 years ago. Why do we expect that this is the one of these three which actually has a finite limit? What is it about the sequence that gives it away? So both an and cn are sequences defined by rational expressions, a polynomial divided by a polynomial, right? And you remember either from pre-calculus or from first semester calculus that a rational function's end behavior, how it behaves as n tends out toward infinity, is governed by a comparison between the degree of the numerator and the degree of the denominator. What's the degree of the numerator in an? The degree here is 1. That's a linear polynomial. And the degree of the denominator? Also 1. And so what's important about that? The degrees are equal. And because the degrees are equal, how did you actually find what was the limit?
Coefficient.
Which coefficients?
The 2n and the n.
Yeah, the leading coefficients, the coefficients of the highest order terms. 2 divided by 1. So if you remembered from pre-calculus, this is probably how you remembered it from pre-calculus. Right? Take the ratio of the leading coefficients. If you remember it from calculus instead, what were some of the tools that you used there? Did anyone do it a different way?
Pulling out the n.
Okay, so we can divide both numerator and denominator by n. There's another way to say that, right? So you pull the n out of the denominator and get 1 plus 1 over n. And then we can cancel the n on top with the n on the bottom. That leaves us with only a 2 on the top and 1 plus 1 over n on the bottom. And then what happens as n tends to infinity? Yeah, the 1 over n bit tends to 0. So we get a 2. Right? That's another algebraic way that looks like something you would have done in first semester calculus. There's one more, if you really want to hit a fly with a sledgehammer here. This is an indeterminate form. It's an infinity over an infinity. And what's the tool from first semester calculus for resolving an indeterminate form? L'Hopital's rule. So we could also have replaced the numerator and the denominator with their derivatives with respect to n. And we would have gotten a 2 on the top and a 1 on the bottom, and it would have been done. But that's hitting fly with a sledgehammer in some ways, right? Great. So we can expect, based on our calculus intuition, that an is a convergent sequence and that its limit is equal to 2. That's important because without having a candidate for our limit, we're not going to go anywhere in the proof. It's one of the harder things about the definition of convergence is it requires somebody to specify for us the value for L. Otherwise, we can't get anywhere. If we don't know what a sequence converges to, we can't use the definition of convergence to prove that it even converges at all. It's one of the limitations of this. And it's one of the reasons why in this chapter we're going to find out ways of getting around that. But we don't have those ways yet, so we have to know what the limit is first. Let's look quickly at this fourth problem. Which one of these three actually diverges to infinity, increases without bound? It's the third one. It's the Cn. And what is it about that one that gives that away? Same reason why the first one converged, the degrees. Because what's important about the degrees of the numerator and denominator this time? Yeah, the degree upstairs is larger than the degree downstairs. And so while both n squared and n minus 1 race off to infinity, as n tends to infinity, n squared gets there more quickly. Right? It goes to infinity at a higher order. And so we expect that this one actually does diverge to infinity. And back in calculus, you might have done the same kind of trick as we were talking about a moment ago, n squared over n minus 1. You might have done something like, well, let's again pull out that n in the denominator. N times 1 minus 1 over n squared, limit n tends to infinity, and then canceled out one of the n's on the top and the bottom. Would have gotten, again, limit of n over 1 minus 1 over n. And as n tends to infinity, this is the same thing as the limit of n over 1 minus 0. The limit as n tends to infinity. That's the limit of n as n tends to infinity. So that's, as we would write it in calculus, that's infinity, right? So this is an example of a sequence which tends to infinity. And so the trick there is to apply that definition from our course to figure out why this diverges to infinity.